Hello everyone. In this video, I will go over my solution for the problem named diamond collector taken from USACO bronze. This problem is an excellent problem which will teach you how to formulate a complete search algorithm using a mathematical observation. The idea of doing some math in order to form observations which will help you to create algorithms is essential to competitive programming, and I'll be explaining how we can do that from the very basics in this video. So in this problem, we are given Bessie the cow who has n diamonds of varying sizes, and she wants to arrange some of them in a display case in the barn. Bessie wants the diamonds in the case to be relatively similar in size, and that's why she decides that two diamonds cannot be in the same case if the sizes differ by more than k. So this means that the two diamonds in the case should have a difference in size of less than or equal to k in order to ensure that they are relatively similar in size. We need to find out the maximum number of diamonds that Bessie can showcase in a given case. And the condition is this thing, that the diamonds in that case should be within size k of each other. So for example, if we are given the input with n is 5, there are 5 diamonds, and k is 3, which means that the maximum size difference is 3. And if we are given 5 integers, which is 1, 6, 4, 3 and 1, those represent the sizes of the diamonds, then the correct answer would be to include the diamond 1, 1, 3 and 4 in one case, because the difference is 4 minus 1, which is 3, and hence the maximum difference is 3, which is less than or equal to k, which is 3. And that's why these 4 diamonds 1, 1, 3 and 4, all these 4 diamonds can be put into one case, and the answer is 4. So the first step in any problem should be to sort the array, because sorting the array is a general technique which you should always think about whenever you're given an array. And in this case, sorting the array is actually the key step, the most essential step in the solution, because once you sort the array, you will realize that if you consider the elements 1, 1, 3, 4, 6, then the key idea is that whenever you consider the condition that the diamonds in the case should have a size difference of at max k, this means that the elements should be something like this. So they could be 1, 1, 3, 4, or they could be 1, 3, 4, or they could be 3, 4, or they could be 1, 3, or they could be 1, 1. Something like 1, comma 6 won't happen, or 1, comma 4 is also not optimal, because it's optimal to include 1, 3, and 4 since we want to find out the maximum number of diamonds which we can fit. So basically, what I'm trying to say is that once you sort the array, the diamonds which you choose will not be random integers from the array, so they won't be a random subsequence. They will actually be a subarray of the original array. So this is the key mathematical observation which you can make. Once you sort the array in increasing order, the optimal subarray, the optimal subsequence will actually be a subarray. And the idea is that always choose a subarray of diamonds, because the elements in the subarray are sorted. So we know that the array is sorted, and that's why the subarray will contain elements in increasing order. And once you look at the elements in increasing order, it's obvious that if you choose the smallest element and if you choose the largest element, then you can choose all the elements between the smallest and largest. And that's why the subarray, the sorted subarray makes sense. So just explaining it in a different way, we realize that if you fix the smallest element L, so let's call this L, and if you pick the largest element R, then all elements from L to R, then all AI then all AI belonging to the range L to R will form a contiguous subarray, in the original array. And this basically means that you can iterate over all the subarrays and check for each subarray whether the smallest minus the largest, which is basically the r minus l value. If that value is less than or equal to k, then you can say that that subarray is a valid subarray, and you can just update the answer to be the max of the answer with the size of the subarray. And this works because let's consider the subarray. So let's say that capital L and capital R refers to the subarray. So let's say that the subarray is from L to R, and let's consider the example of the first sample test case where the elements were 1, 1, 3, 6, 3, 4, 6. Then in this case, what I'm saying is that we will iterate over all possible values of L and R. So for each L going from 1 to 5, and for each R going from L plus 1 or L to 5, so L to N basically. So for each L going from 1 to N and for each R going from L to N, we will check whether the difference, so check if A of R minus A of L is less than or equal to K. If this condition is met, then we know that we can fit all, we can choose all elements. So choose all elements in the subarray from L to R in the range in the subarray L to R, and we can choose all these elements in the subarray L to R because we know that all the diamonds in the subarray from L to R will have a difference of less than or equal to K, because the largest minus the smallest. So this is the largest and this is the smallest. Because the largest minus the smallest is less than or equal to K, that's why all the diamonds in the subarray can form a valid display case, and hence we can just do answers maximum of answer, comma, the number of elements in this range. So the number of elements in this range is R minus L plus 1, because when R is L, then there's one element. When R is L plus 1, then there are two elements, and so on. That's why the total number of elements in this range is R minus L plus 1. And we will update this to be the max with the answer for all the subarrays L comma R, where the largest minus the smallest, which is the maximum difference in the size. If that maximum difference is less than or equal to K, then only we will consider the subarray. And the reason why we are only considering the subarrays, as I mentioned a couple of times before, the reason why we consider only the subarrays is because we know that once we sort the array, all the elements which should optimally be in the maximal case will be in a subarray, because if you won't randomly choose elements 1 and 4, for example, you will choose all the elements in between 1 and 4, and that's why if you fix the largest and smallest, it's optimal to pick all the elements in between, and that's what a subarray means. So this is the idea behind the solution. And what we basically did was, first we came up with the mathematical operation of sorting the array. Then we saw the observation that the subarray will be the optimal case. So the case will always be a contiguous subarray of the original array. It won't be a random set of indices. So it's not actually the original array, it's the sorted array. So the case will be a contiguous subarray in the sorted array, and we just iterate through all possible sorted subarrays in order to find out which case is the largest. And this is the complete search part of the solution, and this takes n square time, because and n square will work because n is up to 1000. So 1000 times 1000 is the number of times the loop will go, and that will easily work in 1 second, because 1000 square is 1 million, which will work in 1 second. And now I'll show you the code in C++, which does the exact same thing. So in the code, first we include bits/stdc++.h. This header file includes all the basic methods you require, and this basically includes stuff like vector, and all the library methods which you require will be imported. once you do the above line, and hence you should always include bit slash std c++.h. You should also use namespace std because that basically shortens the code. You don't need to write std every time. Otherwise, you need to write std vector int whenever you basically use a vector or any other data structure. So to import all the data structures from STL, so this imports all the data structures from the standard template library. You should learn a bit about the standard template library if you want to use the advantages of C++. So you can learn about the data structures uh, from the standard template library, and all the data structures will be imported using this command of bit slash std c++.h. Once you do these two lines of code, you can write the main method. In the main method, the two lines of code are always required for USACO are above. So the above two lines are always required for USACO because you just need to basically input from diamond.in and output into diamond.out. And that's why whenever you use cin and cout, you will be actually taking in the values from diamond.in and printing it to diamond.out. When you want to test the code locally, you need to comment this out, and then you can just uncomment it when you're submitting the code. And now moving on to the main part of the code, where we first take in the value of n and k. So we will use cin and we will use normal integer data type. Then we will use a vector int with one based indexing. So one based indexing is beneficial for many complete search problems, or in general, I like one based indexing. So or you can also use zero based indexing, in which you just iterate through all the indices from 0 to n minus 1 everywhere. And even over here, when you sort the array, you will sort from a dot begin to a dot end. So this is the inbuilt sort method. And then everywhere I'll just change it to zero based indexing. So in the complete search part, we are going for all I going from 0 till n minus 1. Or if you want me to rewrite it in terms of L and R, I can write it as for each L going from 0 till n minus 1. So L is 0 till L is less than n. And for each R going from L, R less than L, we will increase L and R, and we will check whether this range AR minus AL is less than or equal to K. If that is the case, we will set answer to be the maximum of the answer and R minus L plus 1. And answer represents the max size of a subarray of diamonds which form the case that Bessie will display and which have their max difference in size less than or equal to K. So that's what the answer represents, and we'll keep updating the answer with the max difference with the max size of a subarray for all the subarrays which have a difference in size less than or equal to K. So AR is the max diamond size and AL is the min diamond size, and this works because the array is sorted. So it's very important that you sort the array in order for this code to work. And then we just print the answer. You can print it with an endl and return 0 and end the main method. And I'll just submit this code. You need to choose the file. So I'll choose that file and wait for it to get accepted. So as you can see, my code worked on all the 10 test cases, and that's all for this video. So I hope you liked this problem and my solution. If you have any doubts in any part of the solution, including the code, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. In the next video, we will be looking at a more involved example of a complete search problem. So stay tuned for the next video.